So in the last section, we looked at measures of center. We looked at the middle, how close things are in the data. Now we're looking at measures of dispersion. So we're looking at how far away our data is from the center. We have a few measures of dispersion. Now these go pretty quickly here. So there are 5 of them, but don't get discouraged. The first is range. The second is probably the most ubiquitous, and that is standard deviation. So you've probably heard standard deviation before. If you've seen any statistics before, you've calculated it. You definitely have heard it in television and movies. They like to throw this term out whenever they're talking about data and make it into something that it's not. With standard deviation comes variance. And then we also have the empirical rule. Which is really important. And we also have, this guy's got a fun name, it's Chebyshev. He's a Russian mathematician. Chebyshev's theorem. So let's start with range. The range of a data set equals the maximum value minus the minimum value. So it is our most simplistic and basic form of measure of dispersion. It tells us how far the first and last values are. Now this is obviously looking at the ordered array because you need to find the maximum and the minimum. So using the calculator to order your list of data is quite helpful in this regard. So we're just going to calculate the range of this data here. So I'm looking and noticing 44 and 2 are the max and the mins. So our range is 44 minus 2, or 42. And if you're thinking, wow, that seems easy, you're not wrong. The range is an easy thing to calculate. It gives us an idea of how far the data is spread out in general, but not necessarily the best measure of dispersion across that range. So let's talk about the big one, the standard deviation. So the standard deviation measures how much we might expect a typical member of the data set to differ from the mean. So in general, what we're talking about here is, on average, how far away is any one data point from the average? And that may seem weird, but we'll talk about that more as we get through the definition and look at some examples. So our population standard deviation is sigma. Now this is lowercase sigma, not uppercase sigma. So lowercase sigma looks like this, at least how I write it. It's slightly more curvy, I believe, in most people's writing, or even circular. So it doesn't matter to me how you write your lowercase sigma, something that looks close to this. And sigma is the square root, give yourself some space here, of the sum of x sub I minus mu, quantity squared, all over capital N. Now again, x sub I is the ith data value, and mu is the population mean, and capital N is the population size. So this is our standard deviation sigma for populations. We have one for sample standard deviations, and instead of sigma we just use a lowercase s, and this is got virtually the same formula. It's big square root of the sum of x sub I minus x bar, quantity squared, over n minus 1, where x sub I is the ith data value, x bar is the, that should say sample mean, and little n is the sample size. So very similar, but key difference is the sample size versus the population size. We want to go down by 1 here. So let's look at an example. So for this first one, we're going to do it by hand, and then we'll go through how we would do this in the calculator, because we've already seen that sample means pop up easily in the calculator. So this is sample standard deviation. So we're calculating S, square root of x of I minus x bar quantity squared over n minus 1. So we need x bar first and foremost. So 5 plus 8 plus 7 plus 6 plus 9 over 5, and this equals 7. So now when you're doing standard deviations by hand, we typically set up a table to make our work a little bit easier to follow and easier for us to organize. So first column is xi. These are our data points, 5, 8, 7, 6, and 9. The second column is x of I minus x bar. 5 minus 7 is negative 2. 8 minus 7 is 1. 7 minus 7 is 0. 6 minus 7 is negative 1. And 9 minus 7 is negative 2. Or is positive 2, sorry. And then our final column is x minus I minus x bar quantity squared. So now we're squaring the values that we found here. So negative 2 squared is 4, 1 squared is 1, 0 squared is 0, negative 1 squared is 1, and 2 squared is 4. So now we have these values, we just add them all up to fit them into our formula. So S equals square root 4 plus 1 plus 0 plus 1 plus 4 is 10, divided by n minus 1 is 4, or the square root of 5 over 2. And just punching that into the calculator, that's going to give us 1.58, or 1.6 if we were to round off. Now, typically with standard deviations, we want to keep it at 2 decimal places. So let's talk about the calculator side of this, because while this was a relatively small data set, you can imagine if you have 30 data points, you don't want to be doing this by hand. So that's where our calculator comes in. So we're going to go to Stat, we're going to edit our first list, we're going to put in our data 5, 8, 7, 6, 9, and then delete the rest. So delete, delete, delete. So just our values in there. We're going to quit, and we're going to go over to calculate. We're going to do one of our stats. Hitting enter will default it to list 1. So we can check a couple things. X bar, which we've already calculated, is 7, still 7. Our sample size is 5, so we are good here. We can even go down, and if you were checking some of this other stuff, you would check that. So now we're looking at all these different things. So this gives us a couple different information. It sums all of the data. So if you're using a frequency distribution and you're looking for your total, it gives it to you here. It also sums the squares of each of your data point, which is useful in other things. And then here you see S and you see sigma. So the calculator is smart enough, well, I should say is not smart enough to know whether you're doing sample or population. So it gives you Sx and sigma x. Sx is your sample standard deviation, sigma is your population standard deviation. And they are different, because remember, population we divide by total number, here we divide by 1 less. So we compare this, 1.5811 is exactly what we got. So again, for standard deviation, we want to enter our data into the list, L1, and then we go stat, over to calc, and one var stats, and then Sx, comma sigma x are the standard deviations. S for sample, sigma for population. So that's a way that we can do that without having to do everything by hand. Now for small data sets, it's good to know how to do this because you want to be able to understand if you're getting an answer incorrect, what's happening in the calculator. There is one remark we want to say about talking about what standard deviation is. So we think of this standard deviation as the average distance from the mean to a data point. Now, what that distance is actually slightly different. So, in this example, we said standard deviation is 1.58. So, that means that the average data point is 1.58 distance. That distance is in means. So, we'll see more of that in the rest of this section and in the next section. But this is basically creating a distance out of the mean value, out of 7. So most data points are within 1.58 means of 7. So they're up to 14-ish and down to 0-ish. So like I said, we'll get into that in the rest of this section and then the next section as well when we start talking about relative distance and relative position. So let's do a little example of what standard deviation can tell us. So here we have two companies over 1 year of daily closing costs of the stock market, what their stock prices are. So we have company A and we have company B. And so all this question is telling us is to interpret what this means. So we have their standard deviations, S, $1.02, $9.67. So if we think about the mean or the standard deviation, is average distance from the mean, it means that smaller S values tells us the data is more grouped in the center. Because if the average distance is smaller, it means that you have a smaller range that all of those values or most of those values fall into. So if we think in this context, stock prices, the standard deviation of company B is such a larger percentage or such a larger dollar amount that it's probably more variable. And so in terms of stocks, when you're looking to buy stocks, a lot of people invest in safe stocks, stocks that are not going to change too much. So company A has a more stable price in stocks. It means that there's no big swings in their value in that company. Remember, this doesn't tell us what that price is. So just because their standard deviation is small, their mean could be huge. Right? This could be the stock of Apple. Apple doesn't typically have big swings in their stock prices because they're a very stable, successful company. Whereas company B has prices that change drastically, comparatively speaking, compared to A. Right, so this could be, for instance, Zoom in the last 6 months has had a tremendous increase in stock prices because we're all using Zoom now. And even people that aren't in school are using Zoom. So their standard deviation for this year is going to be much larger than what it was compared to last year. So again, this doesn't tell us the whole picture. So don't think of standard deviation as this end-all, be-all statistic. And this is, I said this at the beginning of the section, TV and movies tend to inflate the importance of standard deviation, making it seem like, oh, the standard deviation is this number, and that's really important. Well, it is to an extent. But again, if the standard deviation is 9.67, this could be in the positive direction. So this could mean that more of their data points are actually higher than the mean for whatever reason compared to last year. It also could mean that it's less, and also their price could be lower. So the price of company B, I'm sure it's not selling as well as Apple is, but if we're saying company A is Apple, yes, they have a small standard deviation, but their stock prices are stable, and it's a good investment. They're usually pretty high, and they stay high. They don't fluctuate too much. Whereas company B, they could fluctuate a lot in either direction. Could be positive, could be negative. It could go up in price, they could go down in price. But also their mean price might be really low. It might be $63 a stock compared to Apple's, I don't know, $6,000 a stock. I don't know if that's true. I'm just spitting out numbers here. So we can't interpret it much more than this. Company A has a more, I didn't even write, stable price in stocks. Company B has prices that change drastically compared to A. And that's all we can really say from just the standard deviations alone. If you start adding more information in, we can make more detailed interpretations. So there's you can calculate your measures of center for the Chapter 2 quiz. You have that data. You should be working on that this week as well. It's due at the end of the week. But as a practice, try calculating the measures of center. And if you're watching this, I'll add some extra credit. Let's do some extra credit for including those in your quiz. So for those of you that are keeping up with your lectures and seeing this. So the next measure of dispersion is coefficient of variation. So we have about enough time in this little block to go through the definition, and then we'll finish up the section in the next video. So the coefficient of variation for a data set is the ratio of your standard deviation to your mean as a percentage, so times 100. So coefficient of variation, CV, for a population is sigma over mu times 100. And this is in a percent. And so again, sigma is the population standard deviation and mu is the population mean. For a sample, it's still just coefficient of variation, and this is S over X bar times 100. And this is as a percent. X bar sample, S sample standard deviation, and X bar is sample mean. So the nice thing about statistics is that, yes, every single calculation we have has two versions, usually population and sample, but they're almost always the exact same thing. You just have to remember what they are. It's standard deviation over mean. Standard deviation over mean. Not necessarily standard deviation, population standard deviation, and population mean. So let's pause this section here. We'll finish up 3.2 in the next video.